Alright, in this quick video we're going to look at how to name acids for the Chemistry 30S nomenclature unit. Acids are molecules which produce hydrogen ions in water. That's a very simple definition of an acid. In grade 12 chemistry we revisit this and we get into a little bit more detail than that. Because they produce hydrogen ions in water, most acids are going to have hydrogen ions in their chemical formulas, and almost always those hydrogen ions are at the beginning of the formula. One exception to that rule would be a carboxylic acid. The carboxylic acids, if you've taken some biology, you know that they'll end their chemical formulas with COOH. Okay, so that's a carbon double bonded to oxygen and an OH attached. That's called a carboxyl group. So almost all acids begin with hydrogen unless they're carboxylic acids, in which case the hydrogen may be written like this at the end of the formula. To be a binary acid, just like binary ionic compounds, means that there's only two elements in the compound. So a binary acid will have hydrogen bonded to one other element. Some examples would be HCl, HBr, or H2S. Now look at the names of those three examples, and you'll see a pattern that develops. If you have HCl, now I should point out that these are all dissolved in water. Remember, acids produce hydrogen ions in water. So for binary acids, technically, they should say aqueous, AQ, beside their formulas, if you're going to name them as acids. Without that AQ, you might just think of them as ionic compounds and name them as hydrogen chloride, hydrogen bromide, or hydrogen sulfide, for example. So the first one, these are all aqueous acids dissolved in water. So HCl is called hydrochloric acid. HBr is hydrobromic acid, and H2S is hydrosulfuric acid. Looking at those three names, you see a pattern. The binary acid's name will always take the form hydro something ic acid. And the thing that goes in the middle here comes from the second element in the formula. If you had HI, aqueous, it would be hydroiodic acid. HF, aqueous, hydrofluoric acid, for example. Now you might be wondering why H2S had two hydrogens in its formula, while the other two examples only had one hydrogen in their formulas. That's simply because of the charges on the anions in these acids. Sulfide is S2 negative, while bromide and chloride are each just one negative. Because the sulfide had two negative charge, we added two hydrogens to cancel that out, and you get the formula H2S. So if you have a binary acid, the number of hydrogens is determined by the charge on the anion to neutralize it, and the name takes the form hydro something ic acid. Another broad category of acids are called oxy-acids. These are acids where the hydrogen ion is bonded not to a simple anion, but to complex anions. There are two different broad categories of complex anions. There's the ones whose names end in ate, and that's what we're going to look at here. And there's also ones whose names end in ite. So for example, looking at these four anions, you have nitrate, sulfate, carbonate, and phosphate. So those are all complex ions whose names end in ate. All right, now the first one has a charge of -1, so if you add a hydrogen to that, you'll get HNO3. The second one is 2 negative, sulfate, so it gets 2 hydrogens, and you get H2SO4. Carbonate is also 2 negative, so it gets 2 hydrogens, H2CO3. Phosphate is 3 negative, so it gets 3 hydrogens, H3PO4. Now you look at the names of these four examples, these acids. HNO3 is simply called nitric acid. H2SO4, sulfuric acid. H2CO3 is carbonic acid. And H3PO4 is phosphoric acid. So you hopefully can see a pattern there. if you have an oxy-acid, an acid with a complex ion, and the complex ion's name ends in ate, as we do in these 4 examples, then the acid name is something ic acid. So nitric, sulfuric, carbonic, phosphoric. Okay, those are all the 4 examples that we see here. Now, you'll notice that in these 4 examples, I didn't put AQ beside their formulas. Okay, normally with binary acids, you put AQ to specify that it's the acid you're naming. With oxyacids, that rule is less important. So HNO3 without AQ would still be called nitric acid, almost always. The other broad type of oxyacid contains a complex ion, but this time whose name ends in ite. Okay, so here we have nitrite, sulfite, hypochlorite, and chlorite. Okay, so nitrite, sulfite, hypochlorite, and chlorite. The acid formulas, the first one, HNO2, gets 1 hydrogen because the nitrite was 1 negative. H2SO3 has 2 hydrogens because sulfite was 2 negative. And the last 2 examples, HClO and HClO2, each get 1 hydrogen because their complex ions were 1 negative each. When you look at the names of these guys, HNO2, which contained nitrite, is called nitrous acid. H2SO3, which contained sulfite, is sulfurous acid. HClO, which had the hypochlorite ion, is hypochlorous acid. And the HClO2, which has the chlorite ion, is called chlorous acid. So you can see there, again, a pattern that develops. If you have an oxyacid with a complex ion whose name ended in ite, then the acid's name is something acid. Now, these 2 suffixes that we've just used, ic and us, you might remember that in the naming of the simple ions that had more than 1 charge, the older system of naming reserved the ic suffix for the higher charge and the us suffix for the lower charge of type 2 cations. In a similar way here, we're using the ic suffix in these acids for the complex ion with more oxygen, and we're using the us suffix for the complex ion with less oxygen. Some examples quickly. So on the left-hand side of this table, there are formulas of acids. In the middle column, we're not going to worry too much about that, but if they weren't aqueous, if they were simply named as ionic compounds, and that's how you would name them. And then the far right-hand column, that's the one we're more interested in. If they were aqueous, dissolved in water, they'd be named as acids, and what would be their acid names. So the first example, question 1, if the ionic compound's name was hydrogen bromide, then the formula, bromide we know is a halogen with a charge of -1 or 1 minus. So the formula would be HBr, and assuming it's dissolved in water, aqueous. And then we realize that's a binary acid, has only 2 elements. So its name will be hydro something ic acid. And in this case, with bromide, it'll be hydrobromic acid. The second example, HCN aqueous. If it were not aqueous, if it were simply gaseous, for example, then its name would be hydrogen cyanide. Cn minus is cyanide. Now you'll notice that that's technically not binary, but its complex ion name, cyanide, is named as though it were a simple ion, the IDE ending. It doesn't fall into one of our ate or ite examples, so we're going to name it as though it is binary. So hydrogen cyanide, if it were dissolved in water, would be hydrocyanic acid. And then the last example of binary acids, hydrofluoric acid, if it were just an ionic compound, would be hydrogen fluoride gas, for example. Fluoride is F minus, so the formula for the acid would be HF aqueous. For binary acids, again, it's important to put AQ, aqueous, beside their formulas. Next, we get to the oxy-acids, and this time we're starting off in the middle section of the table with the anions whose name ended in ate. So the first example there was the HClO3. ClO3 negative is chlorate, so as an ionic compound it could be called hydrogen chlorate, but dissolved in water it's now chloric acid. So the next example, H3BO3, BO3 3 negative is borate, so therefore that acid's name is boric acid. Okay, notice again when you have an oxy-acid, the complex ions involved, the acid's name does not begin with hydro. HNO3, NO3 is nitrate, so therefore this acid's name is nitric acid. Permanganic acid must have contained a complex ion because it doesn't begin with hydro. Permanganic, so it must have had the permanganate ion, whose formula I know is MnO4 negative. Therefore, HMnO4 would be the formula of the acid, permanganic acid. The last section of this table contains oxy-acids where the anion's name ends in "ite." So HNO2, the NO2 negative ion, is nitrite, and the acid's name is nitrous acid. So the question number 7, hydrogen chlorite, an ionic compound. Chlorite is ClO2 negative, so this would be HClO2, aqueous, and we have chlorite, so the acid's name is chlorous acid. HClO, that's the hypochlorite ion, so the acid's name, hypochlorous acid. Again, we're not using the prefix hydro because these are oxy-acids. Hydro is used only for binary acids. Sulfurous acid, so there's no hydro at the beginning. This must be an oxy-acid. Sulfurous, it has the sulfite ion, and sulfite is SO3, 2 negative. Because it's 2 negative, we'll put 2 hydrogens, H2SO3, aqueous would be sulfurous acid. All right, let's wrap up with just some more examples. You can pause the video and try these yourself. If you have the name of the acid on the left, figure out the formula on the right. If you have the formula, figure out the name of the acid. I strongly urge you to stop and think, which type of acid is it that you're looking at? Is it a binary acid or is it an oxy-acid? If you decide that it's an oxy-acid, then which type is it? Does it have the complex ion that ends in ate, or does it have the complex ion that ends in ite? Go for it. So the first example, hydroiodic acid, because it starts with hydro, that's the clue that we're looking at a binary acid. And hydroiodic, then it's hydrogen bonded to iodide ions. The iodide is I minus, so hydroiodic acid would just be HI aqueous. Okay? 1 hydrogen because the iodide is just 1 negative. Acetic acid, there's no hydro at the beginning of the name, so that means we're looking at an oxy-acid. Because it ends in ic, the suffix ic, then this was the acetate ion. Acetate can be written in more than one way, but the way I prefer to write it is CH3COO negative, and that's the clue that it's a carboxylic acid. So I'm going to write it as CH3COO, and I'll put the H at the end, aqueous. Now some people think of the acetic acid as HC2H4H3O2. So they prefer to think of the acetate ion in this molecular formula C2H3O2 negative, and they put the hydrogen at the beginning because acids normally have their hydrogens at the beginning of the formula. Either one of those would be acceptable for acetic acid. The next one, HClO4 negative. Okay, so I see that it's not a binary acid. ClO4 is a complex ion called perchlorate. Perchlorate ends in ate, so then the acid's name will be perchloric acid. H2Se, that's a binary acid. It's only got two elements, so its name is going to begin with hydro. That is the selenium ion, or selenide. This is hydrogen selenide if you were to name it as an ionic compound. So as an acid, starting with hydro, selenic acid. It got two hydrogens because selenium is 2 negative. It's in the same family as oxygen on the periodic table. The next example contains a complex ion. It's not binary, so its name will not begin with hydro. C2O4 2 negative is the oxalate ion, so this is oxalic acid. If the ion's name ends in ate, the acid will have the suffix ic in its formula. Bromous acid, so again, not binary because there's no hydro at the beginning. Bromous, so it must contain the bromite ion. Bromite is BrO2 negative because it's only got a -1 charge. We'll put one hydrogen with it, HBrO2, and aqueous. So there you have it. Acids, two broad categories, the binary acids and the oxy-acids. And then the oxy-acids can be broken down into two subcategories. There are some acids which are named as though they're binary. We saw that with hydrocyanic acid because the complex ion's name, cyanide, in that example, did not end in ate or ite. If you have a binary acid especially, it's important to put AQ beside the formula. That way we won't name it as a gas or as a ionic compound. Okay, so AQ is important most especially for binary acids when you're writing their chemical formulas.